Transaction schedule or history. When transactions are executing concurrently in an interleaved fashion, the order of execution of operation from the various transaction forms what's known as a transaction schedule or history. A schedule or history is of any transaction. It's an ordering of the operation of the transaction subject to the constraint that for each transaction Ti that participates in S, the operation of T1 in S must appear in the same order in which they occur in T1. Note, however, that operation from other transaction Tg can be interleaved with the operation of Ti in S. The total ordering. For any two operations in S, one must occur before the others. Must schedule have total ordering. The partial ordering, if parallel process is employed, it's theoretically possible to have schedules with the partial order non-conflicting operation. For two non-conflicting operations to occur in S without defining which occur first. Characterizing schedules based on recoverability. For recovery and concurrency control, interested in the operation. The shortcut for read item is R, and for write item is W. For commit is C. Abort is A, and the additional operation include begin transaction, and the shortcut is B, the end transaction, and the shortcut is E. Example of schedules. Examples of schedule. SA, first thing is read 1x, then read 2x, write 1x, read 1y, write 2x, write 1y. This is ordering operation. The conflicting operation of a schedule. Two operations are conflicting if changing their order can result in a different outcome. There is two types of conflicting. Read-write conflict and write-write conflict. If we change the order of this operation, we will have a different outcome. Here are the examples. SA, first thing is R, read 1x. Read 1x, we'll search for write 2x. This is read-write conflict. Here write 2x, we'll search for read 1x. Write 1x. This is read-write conflict. Then write 1x, we'll search for write 2x. This is write-write conflict. We have three conflicting in this transaction. B, write 1x, we will search for read 1x, we will search for write 1x. SB, the second example, we have read 1x, we'll search for write 2x. This is read write conflicting. Write 1x, we'll search for write 2x. This is write conflicting. In the second example, we have two conflicting, read write and write write.
From this slide, we will going to talk about how we can decide if the schedule is complete schedule or not. From these 3 points, the operation and schedule are exactly those operations in T1, T2 to include a commit or abort operations at the last operation for each transaction in the schedule. That's mean if you have 3 operations in first transaction and 2 operations in second transaction, like this operations inside this table, we need to have exactly the same operations in our schedule. Also, the schedule should to end with either abort or commit. Commit if all operations done successfully, or abort if there is some wrong happened in these operations. Second point, for any pair of operations from this same transaction Ti, their relative order for parents in schedule is the same as their order for parents in Ti. That's mean, let's see this example. This example with this table. Okay, we have here operation with the green color for transaction 1 and operation with the red color for transaction 2. Read 1x, write 1x, read 1y. This green operations for T1, which is read x, then write x, then read y. This same order for operations inside this schedule. Another operation with the red color, read 2x, then write 2x. Here we have read x 2x and write 2x. This order same this. Okay, but if you have operation from different transaction, like this operation with this operation, which is from different transaction, you can't change the order of them. Like here in our example, write 2 should come before read 1 for y, but we change the order of them. It's okay because those from different transactions. Okay. Third point, for any two complex operations, one of the two must occur before the other in schedule. If you have 2 conflict operations, one of them should come before another. We can't change the order of them. Okay, but if the 2 operations is not conflict with each other, it's okay. We can write it with any order because the order is not important in our case. Each transaction end with commit abort operations. No active operation in the end of schedule. Like here, we don't have any either commit or abort. We end with write 2x. So this is called active operation. So our example not scheduling. From this slide, we will decide if the schedule is recoverable or not. We have 3 conditions to check and decide if schedule is recoverable or not. First one, when where no transaction need to be rolled back, so the transaction is commit and roll back for these transactions in the schedule. As second condition, a schedule is recoverable if no transaction T in schedule commit until all transaction T bar that have written and item that T reads have committed. This point mean if transaction 1 write x equal to 1 and transaction 2 come and rewrite this value for x, write x equal to 2, for example, T1 should commit before T2. Why? Because T1 writes the value first. Who write the value first should to commit first. Third condition, transaction T read from transaction T bar in schedule if some item X is written by T bar and later read by T. T bar will write the value and T will read the value from T bar. T bar shouldn't have been apart before T read X. T bar will write the value, for example, X equal to 1, and T bar shouldn't apart because T will read the value from T bar. If the T bar apart, T will not be able to read the value from T bar. And should be no transaction that write X after T bar write X and before T read X. This means if transaction T bar write the value of X and another transaction come change the value of X, then T will write the value, so T will write different value, not from T bar. Why? Because another transaction come and change the value of T bar. No recoverable schedule. That doesn't satisfy the recoverable schedule conditions. If you have a schedule and the schedule not satisfy the condition, these three conditions, so we call this schedule is not recoverable. Let us take some example to make the idea of recoverable schedule more clear for us. We will see the write operation, not read operations, okay? Because no problem with read operations. And first example, this one, transaction 1 write the X, so transaction 1 should to commit first. But we see here transaction 2 commit before transaction 1, so it's not recoverable. Second example, transaction 1 write the X and commit first, okay? And another transaction, which is T2, write X and commit after T1, so it is recoverable. Third example, transaction 1 write the X, then it's apart. Come another transaction, it's also apart. Both of the transaction apart, so we don't need to decide if it's recoverable or not. Cascading rollback. Recoverable schedule where an uncommitted transactions has to be rolled back because it's read item from a transaction that failed. That's mean if transaction 1 write X equal to 5 and transaction 2 and 3 will read this value from transaction 1, then transaction 1 failed, so transaction 2 and 3 should to do rollback. Why? Because if they transaction 2 and 3 continuous, they will have wrong results. This disadvantage of cascading rollback, time consuming based on number of transactions to be rollback. In our example, only 2 rollback. But what do you think if you have a huge number of transactions related or read this transaction 1? You will have huge number of rollback, so it's time consuming. Type 2, cascadeless schedule, which is the second type of schedule, and all cascadeless schedule are recoverable schedule. Where every transaction read only the item that are written by committed transaction. That means if transaction 1 write X, so no another transaction come to read this value until transaction 1 make commit. If transaction 1 make commit, any transaction can read this value, but any transaction can write this the variable until if it's not commit. So we can read, but we can't read, but we can write. This example, no read for transaction without commit. Here we will consider also about the write operations. Transaction 2 write x, then transaction 1 rewrite the value of x, then transaction 2 commit. This example, it's cascadeless. Why? Because no read operation between transaction 2 when they write the value and when transaction 2 commit. If you don't have read operation between this and this, you can't call this schedule as recoverable. No, sorry, cascadeless schedule. Here another example, W2x, so transaction 2 write x, then come another transaction to read this value before transaction 2 commit. So this is not cascadeless, because in cascadeless we can't read the value before committed operation.
Okay, the third type is the strict scheduled. Strict schedule, which the transaction cannot be read or write until it has been committed. It has one advantage: it's simple for recovery by restoring the value of before image. And here is the example. It's not strict because and here it's aborted. And here we have the operations could be recoverable and non-recoverable. The recoverable, it can be cascadeless or strict. Cascadeless, it's cannot read until it's committed, and strict, read and write. And this graph shows the concurrency executing transactions. The three transactions here are occurring at the same point, in the same time also. And the serial schedule, it's a schedule that finish from the first transaction, then will start with the second transaction. There is no concurrency between them. It's disadvantage that it's limit concurrency and waste CPU time. It will be wasting time because it will be waiting the first transaction, then it will start with the second transaction. It can't work with two transactions at the same time.
So now we're going to talk about the schedules that are based on serializability, and we have some examples here to explain the serializability. First thing, we have a rule which said every serial schedule is a serializable schedule, but not every serializable schedule is serial. So here, let's take A and B first, because they have the same condition, which is both are serial because first transaction begins, and when it ends, the second transaction will begin, and the order doesn't matter. So here, because they are serial, then they are automatically serializable. But in case C, the things are different because the schedules aren't serializable. So we have a condition now because they are not serializable, and it's explained here. Now the transaction schedule, we have two types. First of them are serial, and the second is non-serial. If it's serial, then it's automatically a serializable. But if not serial, then it have two conditions. First thing is equivalent to serial schedule, so it's serializable. And if it's not equivalent, then it's not serializable. So here we have several ways to define an equivalence. First, equivalence defining is result equivalent, which means that if we have values for the atoms in the two schedules, and then we tried them or implement them in the schedules, and then at the end we have the same result, then it will be result equivalent, then it will be serializable. But if the values at the end didn't equalize, it will be not result equivalent, then it's not serial. And the second equivalent is conflict equivalent, which means that we have to compare between the conflicts in the schedules, and it will be easier if we use the draw like here. Let's take the first example, which is read 1x, write 1x, then read 2x, write 2x. If all the transactions are hidden to the second transaction, then it will be serializable. But if there is two edges and not all the transactions are hidden into the same transaction, but there is two edges between the transaction, then it's not serial. Let's try with this example. First thing, R1 is heading to right 2x, which is heading to T2. So here we have an edge. Here we have an edge. And right 1 is heading to read 2x, then we have the same edge from T1 to T2. Then in this example it's serializable. Let's try another example. In this one, let's try in this one. So we have read 1x is going to write 2x. So we have an edge from T1 to T2. And the second one is read 2 is heading to write 1. So we have an edge from T2 to T1. So if there is two edges in the same schedule or in the same draw, then it's not serializable. But if we have only one edge for all the transaction, if we have one edge from all the transaction, then it's serial.
Assalamu alaikum. This is an algorithm to test whether the schedules are serializable or not. For this, we will only see the read and write operations, and then we will construct a precedence graph and see if there are cycles or not. A directed edge means it's similar to an arrow. Directed, it has a direction, and it's an edge. A directed graph consists of nodes and edges. Nodes are the ones in which the circles in which we write T1 and T2, and edges are the arrows. For each transaction there will be one node, and there will be a starting node and an ending node, and we will see which one will be starting and from where we will be starting the arrow and where we will end it. For each transaction we will create a node. The second point. The point basically explains if that there will be an arrow from T1 to T2 if there are operations like write 1 and read 2. The third point, there will be an arrow from T1 to T2 if the operations are read 1, write 2. Fourth point, there will be an arrow from T1 to T2 if the two operations are write 1 and write 2. If there is a cycle, then that graph is not conflict serializable, and if it does not have a cycle, then that schedule is serializable. These are some examples of serializable graphs. A, B, and D are serializable, and C is not because it has a cycle.